Tesla poured tens of billions of dollars into supercomputers, mapping billions of driving miles. Yet true Level 5 full self-driving remains tantalizingly out of reach. Meanwhile, a $2,000 plastic box with 3 spinning blades quietly navigates chaotic backyards, dodges running pets, and trims turf with clinical precision. No human hands on the controls. No remote oversight. So here's the real question. It's not, how did lawnmowers beat Tesla? It's this. Why did the easiest 5% of autonomous driving already ship, while the hardest 95% is still stuck in the lab? It comes down to 3 engineering shortcuts, plus 1 computer vision breakthrough. First, the brutal physics of velocity. A car cruising at 65 miles per hour eats up nearly 100 feet every single second. A 200 millisecond delay in spotting a cardboard box on the asphalt means the vehicle already traveled 19 feet blind. At that speed, there is zero margin for error. A robot mower crawls at 2 miles per hour. That single difference flips the computational math completely. Onboard cameras don't need to forecast conditions 200 yards out because time is on their side. When a toddler drops a toy or a dog dashes across the lawn, the local chip categorizes the object and halts the blades long before contact. Slow speed collapses the compute demand, drops the thermal output, and removes the fatal risk almost entirely. But speed was only step 1. The real challenge was mapping terrain with no lane lines to guide it. Autonomous cars lean heavily on structure. Painted lines, street signs, traffic signals. Strip that away on an unmapped dirt road, and confidence collapses fast. A suburban backyard is the opposite of structure. No lanes. Shadows shift by the hour. Furniture moves. Toys appear and disappear. Early robot mowers brute-forced this with buried boundary wire, snaking hundreds of feet under the lawn. Newer models ditched the wire completely, using a system called tri-fusion navigation, developed by the mower company, Mammotion. 3 tracking systems stack on top of each other. RTK, a GPS technique that locks position down to the centimeter, handles open lawn. When tree canopy kills the satellite signal, 3-dimensional LiDAR takes over, bouncing light pulses off the terrain. And when sunlight overwhelms the cameras, AI vision paints every pixel in real time. Grass turns green, concrete turns grey, and anything alive turns red. But the real catalyst behind all of this isn't the sensors. It's edge AI. Self-driving cars often carry trunk-sized computing rigs that lean on constant cloud syncs. Backyards don't have that luxury. Spotty Wi-Fi, no cell tower in range, and streaming high-resolution video to a remote server just burns battery and adds latency. So modern mowers run tiny neural processing chips locally, on under 10 watts. Trained on yard imagery, they don't need to identify the exact brand of a stray shoe. They only need to answer one question. Is this grass, or is it not? And because the environment is locked to a single yard, the model never has to learn the stop signs, highway mergers, or emergency vehicles. It only has to solve one small, repeatable world, flawlessly. That's the actual trick. Car makers are trying to solve an infinitely open world full of unpredictable humans. Mower engineers shrank the problem down to something small enough to solve completely. Keep it slow, stack redundant sensors, and process everything on the machine itself. It's not a gimmick, and it's not proof that full self-driving is secretly easy. It's proof that when you shrink the problem enough, autonomy stops being science fiction and starts being a $2,000 appliance. While Detroit and Silicon Valley fight over the open road, a garden tool quietly solved the one corner of autonomy that was actually within reach. If you find this interesting, subscribe. We explain everyday technology around daily life. Let us know in the comments what we should take apart next. Thanks for watching.